Okay, can you elaborate on what you mean by confused about the whole stereochemistry thing? No is
I understand
okay.
what stereochemistry is, it's chirality, but
Yes.
I don't know. When you say like loss of stereochemistry, like, I'm confused.
Yeah. Okay. So, because when we say loss of stereochemistry, you're right. That is bringing up the concept of stereochemistry. But what that's talking about is back here with SN1.
Okay.
Right?
So it's mostly distress.
It is only, well, stereochemistry is relevant for both, but loss of is SN1. Okay, so we need to make some modifications to our structure because it's only relevant if you have a chiral atom. And if we go through and and on all cases, what we're talking about when we're talking about this reactivity, come on, let me color that freaking carbon, is the carbon that's doing the chemistry. So in this case, what I will go through and do is just kind of color a little green spot on our chiral atom, or on what should be our chiral atom. Okay? But at this point, it's not chiral, so we need to make some modifications. So I'm going to go through and put a hydrogen here. I'll put a CH3 here, and then I'll do a CH2, CH3 up there. Okay? Also on top of which I need to draw a wedge here, and I'll go ahead and put a dash there for our leaving group, so that we now see the full chiral center, right? Because if it's chiral, we need our wedges and dashes. In SN1, and actually we'll take this to the next step. We'll put a bromine in there. Trying to think if I wanted to adjust this a little bit further. So let's start first with our structure. Let's assign R and S. We're going to go through and assign the bromine should be 1, the hydrogen should be 4, the CH2 will be our 3, oops.
2.
Yep. 2, and our CH3 will be 3. If we were to go through and do this, we go 1 to 2 to 3. We're moving in a counterclockwise fashion. So we might say S, except we could redraw it. Our lowest priority must be aimed away from us. And right now, 4 being our lowest priority is aimed at us, so we're looking at it backwards. For me, I don't have to redraw these ones because this is that whole which way is my hand turning. It's just looking at it backwards. So if I look at this and I say that is going counterclockwise, that's S. I'm looking at it backwards, I would call this R. Kind of make sense? Mm-hmm. All right. If we continue this out, for this mechanism, what happens? The bromine leaves. So you're going to attempt to do this. So what we would end up forming is that carbocation. The carbocation is a p orbital, or an unused p orbital, because that central carbon is now sp2 hybridized, because it's lost that last group of electrons. That sp2 hybridization helps to explain the 3 sigma bonds around it, but then what it leaves is this empty orbital where there's no electrons. My nucleophile can now either come in and share to form the bond on top, or it can come in to form the bond on bottom. Since there is no difference between those, both of those are potential products. So it's mildly misleading to draw it like this because, come on, what we should be seeing instead would then be our nucleophile. I don't want to be creative, let's just call it nucleophile. Kind of aimed up. Our hydrogen gets kind of pushed away, and our CH2, CH3 gets pushed down. Everybody okay with that? Okay. And it would be nice if I could draw it right next to it, but I can't. Okay. I also get the scenario where those are now pushed the other direction. Because our nucleophile came in and formed the bond from the bottom.
So it just kind of rotated that.
So I want to be careful. We are not talking about a rotation, and we're going to get to the reason why we can see that in a second. Okay, the nucleophile comes in from the bottom, which then just forces those to kind of push upwards. The nucleophile comes in from the bottom, pushes those to form upwards. This is not a rotation, Because if I take my right hand, you can see my palm, and I rotate it, you see the back of my hand. Right? You say, well, it looks different, but it's the same thing. They're still identical. Okay? If they're identical, when I assign stereochemistry, what am I going to get? If I assign this one as R, and these are identical molecules, what is this one going to be? Also R. Well, let's go through and check. Let's make the assumption that our nucleophile is our highest priority. Typically true, but not always. Okay. Our nucleophile is our highest priority. Our methyl, we said, was 3, CH2, 4. If we look at how we rotate 1 to 2 to 3, right? Okay. That's moving in a counterclockwise fashion, so we'd say S, except our hydrogen is aimed at us, so we're looking at it backwards, so we call it R. What about the top one? 1 to 2 to 3, there's our 4. We're going from 1 to 2 to 3. That looks like we're moving clockwise, but our hydrogen's aimed at us, so that becomes S. Damn. They're different. Okay? Because they're different, we get two possible products. This goes back to that intermediate. So when we say SN1, we say carbocation. Okay? We need to remember that carbocation, because if we remember that carbocation, all these other things kind of stack with it. One of the important things is that nucleophile can come in and attack from the top or the bottom. Okay? Which means I get two potential products. If I had a chiral atom, those two products are now enantiomers of each other. That says enantiomers. Kind of, sort of? Okay, so that's kind of what's happening in here. So what does that mean to us? Okay, well, we started with a structure that was R, and we ended with two products that were mirror images of each other, where half of them are R, half of them are S. We can reference this as a loss of stereochemistry. It's a bit misleading because we say, well, loss, they shouldn't have a stereocenter. We do still have a stereocenter, but we don't have a pure stereocenter. Right? So you could think about it as a loss. I started with 100 R and I ended with 50 R and 50 S. I lost 50 R. Okay? So that's what the loss is referencing. Okay? When you get to a system where you have 50% S and 50% R, left and right hands, we can call that a racemic mixture. Okay? Or racemic products, and that's what that language is referencing. Okay? So when we're talking about stereochemistry, that's what we're kind of concerned about. Does chirality have an effect? Yes. How does that effect manifest in the SN1 system? We end up getting two products that are mirror images of each other. Okay? About the site that had chemistry. And I'll create a system to make it more complicated in a second. And you can frown at me, that's okay. Does that help answer your stereochemistry question?
Yeah.
Okay. Or at least that answers it to me kind of reviewing back. Okay? So what we can then do is say, well, there were other ways that we could do the substitution. Instead of breaking it up into multiple steps, forming the carbocation, we could do it all at once. The nucleophile comes in, makes the bond at the exact same instant the leaving group leaves. This was the pen example. If I've got my pen in one hand with my leaving group, or whatever you want to call Apple Pencil, and I want to exchange for another pen, okay, does it make sense to exchange like this? Okay. Well, both of those pens are representing a bunch of electrons. And if I make the exchange in the exact same location, that's electrons being in contact with each other. That's a bad system. That's eclipse. That's all the bad stuff that we talk about in the previous units that we don't like. Okay? And this is ultimately the hand-wavy approach, but it works. So how does the other pen have to exchange? Well, the other pen has to exchange by coming in as far away from those electrons as possible. So as they can come in, I can push the other electrons out and away. Okay? So when we talk about SN2, the big thing we now need to remember, just like SN1 was carbocation, With SN2, what we're talking about is the electrons coming in from the back side of the bond. So when we think about SN2, everything that drives our direction is backside attack. Okay? Because in our substitution reactions, I'm gonna make a mess. What the hell? Sorry, I got distracted. We'll call the red atom our leaving group, right? And if we looked at kind of this structure, really what we're saying is that those remaining bonds are hydrogens. Okay, so we've got a tetrahedral carbon, 4 bonds, leaving group aimed up. Right? If we come in from the backside, we're coming in, we're going to make the bond here as that one leaves. We get electron repulsion, these bonds then have to umbrella upwards. Does that kind of make sense? We can't do this with model kits because model kits don't allow that flex. Okay, but that's kind of the intent. Right? What would happen if I now put a carbon there? Well, now instead of it being a hydrogen, it's a carbon. What's the difference between carbon and hydrogen? Yeah, carbon has more electrons than hydrogen. So if I bring my nucleophile in, it now has this opportunity where it sees electrons. Well, what happens? That's electrons near electrons, and it goes, yeah, I'm a little scared. And so instead of just having equal open access, it now might flight in a little bit further away from that. Right? So that's going to slow the reaction because it doesn't have as equal access to the backside. If we add yet another carbon, well, now there's even more electrons on the backside, and it becomes more challenging to get in to react. Right? So what does this mean for us? Well, if we're now looking at our substrate, because that's what we're referencing, it's the carbon structure that's running the reaction with our leaving group, we want a substrate that is smaller. Okay? Smaller can be a weird word. If we talk about our substrate, we're talking about the substitution of it, which means we would get back to that nomenclature system of our zeroary, our primary, our secondary, and our tertiary. And under the SN1, we said we wanted tertiary. Why? When we say SN1, we say carbocation. Positive charge, we need more electrons to stabilize it. So we want the tertiary because there's more electrons around it. But tertiary is now very large. I don't want electrons. Tertiary is bad. So if we move to an SN2, we would see kind of our reactivity flip. The zeroary, the primary, and the secondary are all going to react faster than the tertiary. Right? Just like with the SN1, we do address kind of a limit. In the SN1, we said the zeroary and the primary don't react. Okay? We ignore them as far as SN1 mechanisms go because you end up forming zeroary or primary cations, and those aren't stable. Same kind of token happens here. Tertiary does not react under an SN2 mechanism. Okay, so if we're going to try and predict how something happened, and we saw a tertiary substrate, we would say the SN2 mechanism was not valid. We would have to do something else to get it to react. Kind of, sort of? Okay. Leaving group. Leaving group always has to exist. It's always going to be there. We're not going to stress too much about it. Okay. Oops, that was probably a little bit louder than I'd intended. Okay. What allows us to rank leaving groups? As a leaving group, what is it doing? Taking electrons. So for a leaving group to be good, what does that mean it needs to be? Right idea, and you're jumping a little bit. One of its characteristics could be that it's electronegative. Okay, but you're getting kind of specific. The more general term, what does it need to be able to do? It needs to be able to stabilize the electrons it's taking. How do we stabilize electrons? Well, look at the charge first. Is it coming off as a negative charge? That could be a bad thing. Right? Is it coming off neutral? Hey, that's a good thing. Because it's no longer charged, it's more stable. So when we're talking about this good, we're talking about stable. Right? So if it comes off neutral, it's great. Okay? If it comes off charged but it's large, well, that's something that could stabilize it. If it comes off charged but it's electronegative, that could stabilize it. If it comes off negative but it has resonance, that could stabilize it. Right? Which should sound kind of familiar. Those things are the things that we use to evaluate reactivity. It's the exact same principle. Okay? The words that you will find referencing leaving group ability online is that it's a weak base. How do you decide it's a weak base? Charge, size, electronegativity, resonance, induction. All of those same things apply. So calling it a weak base is really just a cop-out to say you don't want to explain why. Okay? Next part, nucleophile. This is a big shift. The nucleophile needs to be strong. Well, what is strong? Negative. The nucleophile has to share electrons. So we want those electrons to be the absolute most reactive they can possibly be. And the first place that we can look to identify whether it was strong is charge. Okay? And our nucleophile donating electrons to be strong needs to be negative. We could go through and we could compare a bunch of negatives. H minus versus O minus. Which one's the stronger nucleophile? Where do we start? Charge. They're both charged. Size. Is there a difference in size? Yes. What's that difference? Oxygen is larger. What does that mean about its electrons? It's better able to stabilize them. Which is the better nucleophile? Hydrogen can't stabilize the electrons as well. Hydrogen becomes the better nucleophile. This is why it's so important to move through those systems and stop reflexing to the things that we typically see for reactivity. You've seen O minus happen a lot of cases. That's because it's incredibly stable. You haven't seen H minus. Why not? Because it's really unstable. It's very, very reactive. Right? So we have to be careful making those assessments because you're basing it off of your past experience. This is where you always go back: charge, size, electronegativity, resonance, induction. Always move through those when trying to explain your reactivity, and you have to think through the action of what it's doing. The nucleophile is donating electrons. If oxygen can stabilize those electrons, that's bad in comparison to hydrogen. But if I compare it to chlorine being bigger becomes the more important thing. Chlorine stabilizes the electrons better. That now puts oxygen to the higher state. Okay? So, nucleophile needs to be strong. Why does it need to be strong? But for the SN1, it donates electrons too. And I didn't need it to be strong. And in fact, if we revert back to the previous slide for our SN1, of course it stepped, weak or irrelevant. Okay? Why in the SN1 was it weak or irrelevant, but SN2 it must be strong?
Why did it need to be weak or irrelevant in the first
Okay,
place?
so let's go back. Why was it weak or irrelevant here?
Oh, because we went through those steps and we were looking at the energy.
For the SN1, there were two distinct steps. Which of those steps was the most important or challenging step to deal with? The leaving group leaving. Nucleophile's not present in that step. It's only present in the next step. That next step is easy. So I don't care about the nucleophile. Because relative to that first step, it's easy. When we move to the SN2, why does the nucleophile become more important? This is all in one step. Everything that's in that one step is going to be important. The nucleophile is now in that step, so it absolutely becomes important. Okay? Why should it be strong?
So that it can happen in the same state.
Okay? So that it can come in and force out the leaving group. What charge was the leaving group?
Well, now it's negative.
Is negative once it takes those electrons. If our nucleophile isn't strong, and this becomes kind of an interesting challenge between this, what we're saying for that strong is actually a relative system. What we're doing is comparing the nucleophile to the leaving group. When we say strong, what we're saying is the nucleophile is more negative than the leaving group. Why? Why do we want that to be true? So it can force the leaving group out. It's a stability argument. The most reactive thing is the negative thing. Negative nucleophile, negative leaving group. It's going to be easier for this reaction to go if the nucleophile is more negative, because it's transitioning to a less negative product. Right? So when we say strong, it's really just in reference to the leaving group. The leaving group is almost always leaving with electrons and is almost always becoming negative, which means the nucleophile is almost always negatively charged because it has to run counter to the leaving group. Make sense? Okay. How do we decide that relative strength? Charge, size, electronegativity, resonance, and induction. All of those things come in again to make that comparison for it. Okay? After that, we can move to the solvent. The solvent does come in and make a play. For the SN1, our solvent was polar protic. Why? When I say SN1, you say carbocation. So everything about the SN1 is dictated based off of the carbocation. Why polar protic? How is polar protic different than nonpolar?
It has polar covalent bonds.
And what do polar covalent bonds generate?
Dipole.
A dipole. What's at each end of the dipole?
What do you mean?
I have a dipole. There's two poles, right?
Yeah.
What's at each end of the pole?
Partial charges.
What partial charges?
Partial positive.
Partial positive and
Partial negative.
what could the partial negative do? Stabilize the carbocation. So for the SN1, I wanted a polar protic so it could stabilize the carbocation. Do I have a carbocation? No. Okay. So what do I want the solvent to do? Well, if it's polar protic, okay, it brings in a large partial negative is not going to be particularly relevant because I don't have any big positives. Okay. But it does also bring in a partial positive as well. Why does that matter? What would that partial positive potentially do? What interacts with a positive? What happens if I use a polar protic solvent? It weakens the strength of the nucleophile. What did we just say we wanted for a nucleophile? A strong nucleophile. If we use a protic solvent, we weaken the strength of the nucleophile. That's not good. That prevents the nucleophile from reacting. So I don't want a polar protic solvent. So hell with it. Let's push the complete opposite direction. Let's go nonpolar. Now nonpolar won't interact with the nucleophile. If it never interacts with it, can it dissolve? Okay. Now what's the problem? If it never dissolves,
It's not a solvent.
they can never interact. That's also a problem. So polar protic kills my nucleophile. Nonpolar doesn't allow me to react. Polar aprotic. So SN1, we picked a solvent to help. Jiminy Christmas. We picked the solvent to help the mechanism. In SN2, we picked the solvent to not screw it up. Okay? Now we get to this super exciting part. Our stereochemistry. What happens with the stereochemistry? Okay, well, again, it would help if we drew something that had a stereocenter, so we'll modify our drawing. This time I can put the hydrogen away, simplify that. Okay? We'll imply that as a CH3. We okay with that? So now what happens? Okay? We run the reaction. The nucleophile comes in from the backside, forcing the leaving group off. Right? This is effectively that umbrella. So as it comes in, it pushes all of these bonds now the opposite direction. So that it looks more like that. Yeah? If I were to draw that, I said yeah and then just ignored you just for the record. Sorry. It just pushes them the opposite direction. Okay? Let's call the nucleophile priority 1. Hydrogen, priority 4. CH2, priority 2. CH3, priority 3. If we move through this loop, we're going, whoops, not nucleophile. That was silly. What's priority 1 on our starting material? The leaving group. The nucleophile will be priority 1 on our product. If we move through 1 to 2 to 3, what direction am I moving? Counterclockwise, so that is S. What happens when I move to the product? 1 to 2 to 3. Clockwise, which is R. What does that mean as far as the stereochemistry goes?
There was a loss of it?
Did I lose it? In the other case, I lost because I started with 100R and I ended with 50R, 50S.
Now you have 0.
I have 0S, but
100%
100% R. So I would argue that this isn't now a loss. I would argue this is a full flip. Okay? Said another way, this is an inversion. We've fully inverted the stereochemistry. We went from S to fully R. And if I started with R, I'd go to fully S. Right? And that is the language we call it. We call it an inversion in stereochemistry. Right? That's a significant difference, right? The SN1, we lost some of our chirality. In the SN2, we don't lose it, we just change it fully over. In the SN1, how many products did we get? 2. How many products did we get in the SN2? 1. Right? So depending on how the mechanism runs, we get different outputs. Right? That's kind of important. Right? I would argue that becomes important in the benefit. Right? One of the complications of our SN1, which I said we'd kind of float on, probably not talking about. I see, give me a second. The benefit here is we don't have to worry about rearrangements at all with the SN2. That's nice. There's another benefit that's not stated here. When you go to make something, how much are you trying to make? I know it sounds kind of weird. If you go to try and make a sandwich, okay, and you make a sandwich and a taco, that's a little weird, right? Your goal was to make a sandwich, and now all of a sudden you made an extra taco. Right? You made something that you weren't setting out to make. In the SN1, what happens? I have a goal to make a product, and I get 2. In the SN2, I set out to make a product, and I get a product. Synthetically, the SN2 is much better because I make one thing, not 2 things. Okay? Yeah? Though always becomes dangerous. Okay? If we have a chiral atom, yes. If we don't have that chiral atom, we will always produce 2 nucleophile attacks. Okay? And this, when we talk back to our chirality chapter, I said we need to establish the relationships between structures. This is one of the reasons why we need to establish those relationships between structures. For SN1, the nucleophile can always attack top, it can always attack bottom. So in that respect, there's always 2 possible outcomes. To decide whether there are 2 products, what do you have to do? Compare those 2 outcomes and decide, are they different? Okay? Or rather, are they not the same? If they're not the same, then yes, it formed two products. If they are the same, there were still two possible ways to get there, but it ended at the same point. There's just one product. Okay? And that really comes into play if you start with a stereocenter. If you don't start with a stereocenter, there's still two ways to get there. You just can't tell the difference which way it went. Does that make sense? Questions? Okay. What we now, actually not quite what we now move into. So one of the things that you're going to be responsible for, and actually I think I can back out of this real quickly. Actually, I'm not sure I gave you any questions like this yet. If we open up the practice, let's see if I gave you questions along these lines yet. Here, look at question number 2. Okay. Question number 2. I think this works. It's not quite as dramatic as I wanted, but it'll work. Here, we'll make it more dramatic. Delete, delete. Here's the drama, okay? Theoretically, what you will be asked, not a whole lot of times, but I will ask it, is what's the product of this reaction? Or products, plural. So what you need to be able to do is to look at this and say, that's going to follow an SN2 mechanism. Because it's SN2, I only get one product. That's going to follow an SN1. That means I have to identify two products. Okay. Officially, we have to have a stereocenter, so we could throw a methyl group on there. Okay, we're going to ignore this first one for the moment. We go dink, dink, dink. Yeah. Okay. So when we look at this, how do we know? Because if it's SN1, what's our answer? I get two products. True. But again, I ask, what's the answer? Actually, no, that one was actually okay, interestingly enough. What's the answer? Which of those is my product if this is SN1?
2 and 3.
Structures 2 and 3. The leaving group leaves, leaving behind a carbocation. The hydroxide, the negative oxygen, can come in and share either on top, forming the wedge, or it can come in from the bottom, forming the dash. 2 and 3 are the valid answers. But what if it follows SN2?
Then it's only going to be one of those answers.
I only get one product. Well, in SN2, when I say SN2, you say backside attack. Where's the backside of a wedge bond?
Behind it,
Okay, how would I draw behind it?
the dash,
A dash. So if I run this as an SN2, where's the OH?
on a dash.
On a dash. My answer is only 2. Make sense?
Yeah.
Okay. So how this question has been altered to or phrased is you now have to decide which is true. Why is answer choice 4 here?
Where did the second hydroxide come
Yeah, okay, good. Where did the second how would the second hydroxide get in there? That's an awesome statement. You don't understand why it would be there. What you've already said by making that statement is you understand the chemistry. Phenomenal. Okay, so for the sake of this, let's just ignore that. Okay, so how do we know it should be doing 2 and 3 or just 2? How many curved arrows? How many curved arrows are shown?
I meant like reaction arrows.
That's looking at the mechanism. That's again curved arrows. All I'm asking for is the product. How do I know? Well, what I would have to do is go back to those 4 characteristics for my substitution reactions. Those 4 characteristics are solvent. No solvents given, so bad choice. Try again. Nucleophile. What do you see for a nucleophile here? True. How do we classify our nucleophiles? SN1 versus SN2.
One is strong.
SN1 was weak. SN2 is strong. What kind of nucleophile do I have?
In relation to the leaving group, it's strong.
It's strong. If I've got a strong nucleophile, that suggests SN2. That starts to say that I should be just saying one answer, structure number 2. Okay, there's 2 more pieces of things that we should be looking at, one of which is useless.
Leaving group.
Leaving group, we don't care. Substrate. Okay, the substrate. Okay, so we go to our substrate, which is our alkyl iodide. Okay, we look at the chemistry, the position where our iodine is connected. We look at that carbon. We say how many carbons are connected to it. 2. We have a secondary substrate. Is the secondary substrate favored in either one of our mechanisms?
No.
No. So the substrate was utterly useless. Okay, substrate wasn't useful. Leaving group wasn't useful. Solvent wasn't useful. The only thing we've got left to look at is the nucleophile. And our nucleophile, we said, was strong. So based off of that information, which mechanism do we think we're doing? And if we think it's an SN2 mechanism, what's our answer? 2. That's the answer we go with. All of those thought processes need to be moved through. What's the question? Or are you just like, that's too much? Okay. It's too much right now. You haven't had enough practice with it. You need to start building up that practice on recognizing those patterns behind it. Okay. That level of question I shouldn't be asking a lot of, because that is asking a lot of you as a student for someone that doesn't get to practice this anywhere near as much as someone taking the full year of OCHEM. Okay? So more likely what you would see would be how the initial question is. This follows an SN2 mechanism. It's SN2. What should happen? I should do a substitution. 4 is wrong. 1 is wrong. Between those 2 answers, arguably a trash question, but okay, it should be 2. Why is it a trash question? What's the difference between structure 2 and 3?
Where the OH is located. I mean, it's still located on the same carbon, but direction is pointed.
The orientation makes perfect sense when what kind of carbon do you have? A chiral carbon. Is that chiral?
No.
No, this is a trash question. Okay, it needed to be a chiral carbon to see a difference between structures 2 and 3. 2 and 3 are identical molecules. When we're calling this SN2, you should be saying 2. Okay, but yeah, the question should have been written much, much better to prevent that kind of interpretation, because 2 and 3 are identical. Yeah, it's just a flip of the molecule. Okay, which is why inadvertently I saw it, I didn't acknowledge it, but what did I quickly do? I added a methyl so that we could see that it was chiral, because now there's 4 distinguishable groups, whereas before there was not. So I acknowledged it, I just didn't process it. Kind of make sense?
Yeah.
Okay. So, close this. We'll go back to the slides. So that's what this is attempting to kind of set up. Okay. What this provides is now a summary of SN1 and SN2 with respect to all of our patterns. Okay. So substrate. SN2, the fancy word is steric hindrance. That's electrons on the backside. That's all it means. Okay? SN1, I care about carbocation stability. Nucleophile, I want a strong nucleophile for SN2. For SN1, generally weak nucleophiles. Notice I changed the font. Why did I change the font? It's not as important. When we moved to the leaving group, really changed weird font, small font, italicized, because it's not useful at that point. We don't need to look at it. Substrate patterns, there's our zero-ary, primary, secondary, react faster for SN2. For SN1, tertiary reacts faster than secondary. There's our polar aprotic, our polar protic. Stereochemistry, inversion, racemization, conjugation of that fancy word. Okay? And we could look at the rates. I don't think I'll ask questions about rates, but we've already kind of touched on that when we talk about what was important in each of those mechanisms. In the SN1, what was important? The leaving group leaving. Where was the leaving group connected? To the substrate, which was our alkyl halide. So the speed of my reaction was only dependent on the substrate. We moved to the SN2, what happened? Nucleophile attacked the substrate all at once. Alkyl halide is my substrate, there's the nucleophile. They're both dependent on the rate. Kinda? Okay. Ranking kind of importance. So sometimes I modify the slides, sometimes I forget to. For me personally, I focus at the nucleophile. The nucleophile is almost always my source of electrons. It's what's doing the attacking. So when I look at a reaction, I find the nucleophile. I find my electron source. It's typically the one that's charged. So that's where I start my focus. Then I move to the substrate. Okay? I might, if I need to, look at the leaving group, but that's usually pretty low priority, and we'll talk about a scenario where that matters. Okay, I'll actually draw up an example. And then if I really have to, I'll look at the solvent. Okay? But the only reason I'm looking at the solvent is because the nucleophile wasn't helpful, the solvent and the substrate wasn't helpful. So now I'm forced to answer a question about the solvent, which is really just, did I memorize polar aprotic for SN2 or protic for SN1? Kind of make sense? Okay. We ready to look at why leaving group would matter? Cool.
Wait, really quick.
Yes.
What did you say that steric hindrance was?
Steric hindrance is just electrons getting in the way.
Okay.
So
again.
backside attack.
Okay.
Yeah. I should really be saying backside attack there as the phrase reference, because you'll note I don't have carbocation and I don't have backside attack in this list,
Yeah.
but those should be the big call outs.
Okay.
Are you still copying that, Alina?
I got a picture, thank you.
Okay. For the record, everybody realizes you have access to the slides, right?
Yeah.
Okay, just checking. So we saw that example with the alkyl halide, right? Where we had that with what was, I already forgot what it was. Was it chlorine? Was it iodine?
It's iodine.
Thank you. Wedged.
Mm-hmm.
Okay. And we ran that reaction, the iodine left, all that fun stuff. Cool. Okay. But remember when we talked about our introduction to this, we said we could look at alkyl halides and we could look at other functional groups. So let's look at another functional group. Let's look at the functional group of an alcohol. And if I were to generically look at this system, I don't know within that box for this point, because I don't care necessarily SN1 or SN2. That hydroxide would have to take the electrons away. When we looked at it as the iodine, it was I minus, right? Would I predict the same speed, per se, with this new reaction? Why not? Say it again. Negative with a what?
It's a different solvent.
There's no solvent. I haven't specified that.
Did you say would we predict the same speed of reaction?
Mm-hmm. Again, question mark, I don't know what's going on in there yet.
I mean, I guess it depends on how fast the leaving group takes the electrons.
Yeah, it's going to depend on the ability for the leaving group to take the electrons. Awesome. So, push.
Is oxygen more electronegative? Because it's right next to more.
Oxygen is more electronegative than iodine.
Okay. Iodine is bigger.
Ah, cool. So if oxygen was more electronegative, you'd say it's more stable. But you said iodine is larger, which means it would be more stable. Which one's more important, size or electronegativity? Size. This is why we talk about that list. Charge, size, size is more important. So which one of these would we predict to go faster? The one with iodine. Yes. Okay. So what could I do to speed up the top one? Okay. What comes before size? Charge. Could I ensure that when this left, it wasn't charged?
Yeah.
Okay.
Wait. On the reactant side, positive.
How do I make it positive? What would it have to do on the reactant side to make that oxygen positive?
Not have electrons.
So I'd have to get rid of a pair of electrons. Ooh, can I do that with an oxygen?
Not really.
Kinda not really. Not really. I can't have an unsatisfied octet. It must have its octet. But if I had that connected to another atom, ooh, that would be fair game. What should that other atom be? Okay. Now what would happen? Now as it leaves, what is it leaving as?
Neutral.
Neutral. Is this now a good leaving group?
Yeah.
Yes. So when we look at the alcohol functional group, the alcohol functional group produces a hydroxide leaving group. That's not a good leaving group. So what we end up doing is what some might call an activation step. We, instead of having that oxygen act as a leaving group, we ensure that it picks up a hydrogen from somewhere. What kind of chemical reaction happened here?
Acid pairs.
Ooh, good. That's an acid-base reaction. Okay. As an acid-base reaction, what did our starting alcohol act as?
The base.
The base, because what happened? It accepted a hydrogen. So for my alcohol to do a substitution, almost universally, what do I have to add as a chemical?
Acid.
An acid. So for our alcohols, you'll almost always see some type of acid also included in that reaction. Why? So that you can protonate the oxygen to form the good leaving group so that it can run the chemical reaction. Phenomenal. Make sense? Okay. What other functional group do we talk about? What functional group is that?
Ketone? No?
Like a seal. E, 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 e.
Don't think that's helpful. I don't know.
That was a pretty decent hint.
Starts with an E.
Yeah, there we go.
Oh.
It's an ether. Come on, that wasn't that bad. How many of your teachers act out being a seal? Okay. If we look at the ether functional group, if we just left it alone, would that have been a good leaving group with the negative charge? No, it wouldn't. So for an ether functional group to react and do a substitution, almost always what do you have to add? An acid, just like you did with the alcohol, so that you can protonate it so that it comes off neutral instead of negatively charged. Okay? So we can modify the functional groups to make them better leaving groups. Kind of makes sense? Clear this all the way. You okay with that? Does anybody want to copy that? No? Okay. Let's show something gross. Let's just go all in. Would I expect this to do a substitution reaction?
No,
Why not?
it's not a good leaving group.
What's the leaving group?
I guess either side of the O on the, well,
Either side of the O, let's push on that a little bit. Okay. Do I expect the electrons in that bond to go with the carbon?
no,
No. Why?
it's carbon,
Not good enough.
because it's less electronegative.
There it is. Carbon is less electronegative than the oxygen. The electrons in that bond will only go with the oxygen, which then means
The top is the leaving group.
the top part is the leaving group. And you're telling me that if that oxygen stole those electrons, that would not be a good leaving group. What?
SN2.
You just said it's not a good leaving group. Why? And maybe to kind of help.
For the same reason that OH wasn't a good leaving group.
Okay, so elaborate. That's a question mark. OH wasn't a good leaving group because why?
I mean, it wasn't a good leaving group.
Why?
because It ended up negative.
It didn't stabilize the charge very well. Okay, why not? Well, it's just oxygen. Charge, size, oxygen. There's no difference, man.
Resonance?
This structure has a wicked amount of resonance behind it. What does that resonance do to the negative charge?
Stabilized.
Stabilizes it, which means
It's a good leaving.
it's a good leaving group. Okay? What I want you to be able to do is to process through those secondary pieces. Okay, to look at a structure and say, okay, I want it to leave, let's have it leave. What do I think? Is this good? Is this bad? And run through that order. Charge, size, electronegativity, resonance, all that, and try and process that. I'm looking for that logic pattern. Okay? The other out, okay, the other way to get through this, instead of processing a logic, is to do what? Rote memorization. Okay? And when people complain about OChem, it's because they never bothered to learn, or they were never bothered to be taught how to process the logic. Does that make sense? You get to decide. We are very quickly approaching the end of the semester, and you have to find a balance between memorization and application. Right? And I hope to split the exam fairly well so that you could get half by rote memorization and half by application. So that theoretically, if you are strong at one, you can be a little bit weak at the other and still do well. Does that make sense? That's hard for me because I hate memorization. But that is something that I'm going to attempt to try to do as we build out the exams. Okay? Okay, so cool. We looked at some interesting new examples. After that, what this is now moving into, I'm calling these the online slides instead of play pause it because only one of them was a play pause it. Okay? We get our basic, I don't like using the, I need to start calling it core elements. Okay, or our core components. We've got our substrate, leaving group, nucleophile, and our solvents. Okay? This slide kind of summarizes those big kind of topics that could go with it. You'll hear a reference to our zero row primary, secondary, tertiary. You might hear a reference to sp2 and allylic. What would be an sp2? Let's take a look at the substrate that's drawn immediately for us. Is that zero primary, secondary, or tertiary? We look at where our leaving group is located. That carbon is connected to how many other carbons? One, which means it is primary. What does sp2 mean?
Connected to 3 things.
3 things. How many things is that carbon connected to?
4.
4 things, because we have the 2 hydrogens, right? If we're going to say sp2, it has to be connected to 3 things. So we can get rid of one of those things. But then what happens?
It's a carbocation.
It's missing its octet. It still needs to have its octet. What do we need to bring in? Double bond. That is now what I would call an sp2 carbon for our leaving group. Okay? sp2 carbons don't react in these mechanisms. Okay? Very unstable. They don't work in SN1 or SN2. Not very unstable. That just, and unfortunately pushes out to molecular orbitals, and you don't want to talk about molecular orbitals, so this would be something I would just memorize. Your sp2 carbon does not react. Okay? So I want it in the list of things for sp or for our substrate because it could show up. But what I want you to remember is that it doesn't. Does that make sense? Okay. You'll note that we also have another fancy word out here. We have a fancy word called allylic. Okay. Allylic, interestingly enough, is talking kind of about the same concept, our sp2. But it's talking about the sp2 in a different spot. It's talking about the sp2 over here. Okay. The carbon one further away from our leaving group. Okay? How would that change things?
I don't know, you always say not to look over there.
You're right. What's that? It turns out it isn't irrelevant. Okay? In an SN2, 100% yes, you should say it's irrelevant. Because in the SN2, is there anything that could have any effect really out here? Maybe a little bit of sterics, but that's about it. Okay? Why would it matter for the SN1? What is the SN1? When I say SN1, you say carbocation. Why would it matter with a carbocation? Different R. Resonance. The allylic position allows for resonance. Okay? That resonance now becomes a really big deal because what does resonance do to the positive charge? It stabilizes it, which then means very reactive in the SN1 mechanism. So what we need to be able to do is not only recognize sp2, zeroary, primary, secondary, tertiary, but we also have to recognize, particularly as it comes to the SN1, that we can do resonance stabilization through what's referenced as the allylic position, right? Or allylic chemistry. What is the allylic position? It's a little bit weird. Okay? The allylic position is referring to that carbon. This is allylic. Sigma bond, pi bond. If you're in that distance, that's allylic. You could also hear reference to something known as benzylic. It's a nomenclature thing. I wouldn't stress too much about it. But that now big ring structure is a benzene. Okay? Note where our carbon is. Sigma bond, pi bond, right? So why don't we call it allylic? Well, because it's connected to a benzene, so we call it benzylic. That's just people having fun with naming. Okay? Trying to recognize the difference in those reactivities. So ultimately, what does that mean? Allylic carbocations are more stable than our tertiary, which are more stable than our secondary, more stable than our primary. The allylic just means that it's one carbon away from a pi bond. Does it say necessarily how many carbons are connected to that allylic position? No, it just says that there's a pi bond one away. So I could have, in this case, a primary allylic because that carbon is only connected to one other carbon. I could also have a secondary allylic. I could also have a tertiary allylic. Is secondary allylic more stable than primary allylic? Yeah. It's now a stacking effect. Right? You're looking at a substitution effect and a resonance effect. Your leaving group ability, it's your atoms that take the electrons. Okay? If we think about bromine versus chlorine is really just there as the example. It's which one can stabilize the electrons better. This is dealing with our charge size, electronegativity thing again. Nucleophile versus base. This becomes challenging. Right now, we really only care about nucleophiles. Next week, we're going to bring in them acting as bases. Okay? Because it's not just as simple as SN1 and SN2. We also have to worry about elimination reactions, because elimination reactions have the same basic pattern of reactivity. We'll have to nuance the difference between nucleophiles and bases. H and M.
Yeah, what is MH mean there?
Oh, sorry. I had to find the context right up here. M for Metallica.
Really?
Pantera. Nobody?
I don't think that's
Metal?
what it stands for.
Oh.
Oh.
Come on, I like metal. Metallica? Pantera? No, fine, whatever. If you're looking at a metal, what kind of bond would this be? Ionic, which means what's the nucleophile?
Non-metal.
Yeah, it would be a nonmetal. It's always going to be a nonmetal, though. If that's an ionic bond, where do the electrons spend their time?
Near the
Near the nucleophile, which means what charge is the nucleophile?
part. Oh, negative.
Negative. If M is metal, we get SN2. Why? You got a strong nucleophile. If it's H, that's now a covalent bond. As a covalent bond, I don't generate the negative charge. It's now weak or irrelevant. That's our SN1 mechanism. So it's trying to recognize or generalize it enough to allow us to apply out. Then our solvents, we've got multiple definitions for our solvents. The only two you care about are protic and polar aprotic. Kind of, sort of? Okay. That's the end for that summary. After that, it's now really pushing into all the specifics of each of those names, what those things mean, yada, 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 how you stabilize, all that fun stuff, some energy diagrams. Yay, you could look at all that. You'll hear a reference to Zaitsev rule. We'll talk about that later. Then we move into the leaving group ability. For those people saying I'm going too fast, watch the videos because the videos actually talk about it. I don't want to talk about it here because it's already there. Okay. I do apologize because you'll see the text doesn't align well. This is a copy-paste issue. You're welcome to make a copy of the slides and modify those so that you can see that language. I do apologize for that. As you watch the videos, you'll be able to at least see the stuff nicely. It's just the copy thing with a problem. Solvents, we get back to our fun solvent tree, protic and all that fun jazz. More practice with identifying all those things. Okay, what things we need to worry about, all that kind of fun stuff. Our nucleophiles versus bases. I will point out down here, the video is going to spend some time talking about these harder rankings. Nucleophilicity and size. Okay, so when we talk about charge, size, electronegativity, figuring all those kind of pieces out, okay, size does play a role with nucleophilic character. However, there is a massive solvent dependence. What do I mean? Okay, you can take a large species or a large nucleophile and it will be a weaker nucleophile than a smaller one, or it can be a stronger one than a smaller one, depending on what solvent you're in. Okay, that sucks. Straight up. Okay, in a full year course, I think I ask one question. I don't think I will ask you ever a question dealing with that on an exam. I think I float a few questions in the weekly practice. Okay, just because I want you to at least have some exposure to it. Just realize it really does stink. Okay? Nucleophile solvents, this is where it's explaining that difference. And then this is nucleophile versus base. Nucleophiles donate electrons. What do bases do?
Oh, wait, sorry.
They accept H plus by
Yeah.
doing what? Donating electrons. So nucleophiles and bases do the exact same thing. Okay? Because they're doing the same thing, it is very easy to confuse them. The video will go through and talk about a few cases and how you would try to evaluate and decide what it's doing. Okay? There are some cases where you can see a species that acts solely as a nucleophile or solely as a base. The video does address those. They're really rare, and I wouldn't spend too much time actually memorizing them, and I'd focus more on what their general chemistries were instead. Substrate effects, so we start applying now substrates. Whoops, nope, never mind, that's not online anymore. Okay, substrate effects, okay, looking at applications. So if we move through these, how are these substrate effects going to manifest? Okay, so let's take a look at that very first structure. If we were going to run a substitution reaction, so we'll just say SN, S for substitution, N for nucleophilic. We're not specifying 1 or 2 because in this case I want you to kind of think through, looking at this substrate, which mechanism is most likely. So we're going to react it with a nucleophile, and we're going to get the result where we now have the nucleophile connected and we've got the hydrogens on. For those people being, oh, you've already tipped me off that I know this must be an SN, or it can't be an SN2 because the nucleophile has to come in from the backside, so the nucleophile should be written on the left, not on the right. It's irrelevant because carbocation assumes SN1. That carbon is not chiral. So left versus right is irrelevant. Okay? We also got to be careful about making assumptions of left versus right because I could take the structure and just spin it. The spinning of that structure is something you're responsible for acknowledging, doesn't change the overall chemistry. Okay? So since it's not chiral, it doesn't matter. So if we were to look at this as an SN reaction, which SN would we predict?
SN2.
Why SN2?
It's 0.
This carbon is not connected to any other carbons. Okay? So the backside is very open. So a strong nucleophile should come in and be able to access the backside very easily. That would suggest SN2. Okay? So I can agree with that. SN2 makes sense. The backside is accessible. Why not SN1? Why can't it be both?
Because that doesn't, in SN1 you can't have a 0.
This is where when we talked through them in our SN1 and SN2, I went through and said, these don't happen. Zeroary does not form cations. Since this is a zeroary structure, because it's not connected to any other carbons, this does not run in an SN1. It only runs in an SN2. Next one. Still SN. I'm not going to draw the product this time.
SN2.
Why do you say SN2?
It's a primary carbon.
Okay. We've got our carbon where our chemistry we would predict to occur is only connected to one other carbon. That would suggest it is a primary, and primary only reacts under SN2 conditions. Not you. Next one. SN what? What was our approach to the first two? We didn't necessarily look for a carbocation. What did we look at? I accept the first part of your statement. Carbo, I accept. I don't care about cation yet. Carbo. There we go. That carbon where the halogen is connected, that's the reactive one. The rest of this is effectively nonsense. Okay, so that's where my focus needs to be. Okay, to decide which mechanism, I need to know what that carbon is connected to. So now I can selectively move out to see what it's connected to. It's connected to what? Two other carbons. Okay. Are those carbons allylic? Whoops. Are we in a allylic system? Do we see a double bond? No. So we're really only looking at this as a secondary halide. What mechanism does the secondary halide favor? What? You are half correct. The secondary halide, you should acknowledge when you see one show up on a test, this sucks. Because the secondary halide favors both. It's effectively a non-answer. It doesn't help you to distinguish one versus the other. Okay? Last one. You can chime back in if you really want to. We again look to the carbon where our electronegative element is connected, our polar covalent bond. We say how many carbons is it connected to? 2, 3, which makes this tertiary. Is there a preference for the tertiary? SN1. Wow, that actually worked. Make sense? And we're done. We will finish out our substitution next week or on Tuesday, and then we'll start into the elimination. The elimination is going to use a lot of the exact same principles. You're now just going to change some of the dynamics to change the outcome. Right?
What do you think the exam will be?
I do have it in the lecture schedule. If you check the Unit 3 lecture schedule.
Okay.
Actually, here, let me actually pull it up. It was useful to go ahead and include in the recording. Modules. I guess it's in lecture recordings.
Thursday.
Week 13.
Okay.
So we finished today, so not next week, but the following.
Okay.
Yeah. And I think I need to hold to that pretty hard,
Yeah.
just of where we're at with our timing.
Yep, yep.